Okay, so let's get started. There are a few guys sort of like checking in, but that should be all right. Okay, so welcome back. Well, not welcome back. Yeah, welcome back to the third class of Generative AI, Literacy and Application. Now, last week you had a glimpse, I think, a taste of what it would be like to basically build some kind of well, AI program, so to speak, sort of like a hello world kind of thing, right? And I think Marco was using Colab as an environment. What's good about Colab is, well, first of all, it's free, always free, and it's a big community. It's a very large community, and so it motivates people who like to share their algorithm, their method, or whatever, to just kind of like publish it as a Colab notebook, so to speak, right? So that's good. That's good. Um, this semester, we'll try to get you to have a hands-on experience with quote-unquote coding. Okay, when I say coding, it doesn't mean heavy-duty coding like you guys might have the impression of. So it's going to be fairly easy or top-level descriptive kind of thing. Okay, but we'll try to use different platform. Last semester, when we focus on what's called agentic workflow in agentic AI, which some of you may have heard of. If not, we'll go over that anyway. We try what's called a Diffie platform. Okay, Diffie is one of those platforms that's kind of like user friendly. So Marco and I and Ajahn Gongkan, who you see later in the semester, we always try to balance between realism in the sense of what it would take for you guys to actually play with this stuff, right? In a non-trivial setting, but in a way, try to get you on top of the game by playing with a platform that's kind of a bit more user-friendly, okay? So in other words, the course would be quite different if you guys were, let's say, second year computer science major or something like that, right? So we try to make that so bear that in mind, that's what we try to do. Now, it doesn't make everything all easy, right? But please just keep in mind that we try as much as we can to give something that would appeal as well as be manageable by someone who's not a real coder by any chance. Okay, so let's to get the class going today. Okay, the first bit I plan to actually take maybe no more than half an hour, maybe 45 minutes. I'd like to review a little bit about our common understanding, which was something I hope we established from the first lecture, right? So the idea is, well, we talk about I, right? We talk about I. And so it's a little bit of a review, okay? So you can think of this as a bit of review as well. And maybe about 20 of you weren't here in the first class. So might be a new material, but then you can talk to your friends, and hopefully the other 80 people will try to fill you up on what you missed, because the 20 of you were doing the camp, the orientation camp for the new batch. Okay, so what's very important about the first lecture is I write GAI backward. I start with I. Okay, so the concept of I, which again, three concepts, right? What's the first concept of I? I'm not going to write. I'm just going to say it because it's a review. The first concept is I, just being human being full of ourselves, right? We call ourselves the most intelligent animal or the most intelligent species on Earth. So anything that's like us, we consider that intelligent. Okay. In fact, there's no reason why science fiction would have Martian would have appearance like human, except we consider them to be intelligent alien, and therefore they probably look like us, and they have 4 arms and legs. And if you think about it, we are the bilateral symmetric body plan is very universal, but this kind of head and two arms, and that's really just us, right? Tigers don't look like that, lions don't look like that. Anyway, but we kind of like are self-centric. So anything that looks like us, we consider it intelligent. Okay, so the first meaning of intelligent is human-like. Okay, we equate human with intelligence. That's it. A second meaning of intelligent, which some of you, a lot of you actually, graduating from Basai would probably go on to do maybe management consultancy. Then you will see things like business intelligence, right? Now, business intelligence, if I remember correctly, I did give you the background that it's a borrowed term. You borrowed the term intelligence from military intelligence, right? Except with military intelligence, the information in Thai called khao grong. It's kind of like in-depth information, expensive information that has to be filtered, has to be gathered. It's very expensive. You paid for it with your lives. Okay. The difference between business intelligence and military intelligence tend to be that with military intelligence, your focus is largely on your enemy, right? With business intelligence, your enemy, i.e. your business competitor, is just one group that you want to get intelligence on. The other group of intelligence is your client, right? Not your enemy, your client. If you have a large corporation, even your shareholder basis, right? Investor base, that's also the cohort that you want to understand. So the intelligence on what the market, the investment community thinks about you, right? And the investment community is not your enemy, certainly. In fact, they're the one financing your enterprise. And then, of course, finally, we have business intelligence that has to do with information about your own workforce, right? Right? How happy they are, what motivates them. Are they going to jump ship and join your competitor with just 30% rise in pay, right? Or you're such a good company that somebody offers your employee 50% rise to go work for the competitor, and they'll say, no, I'm happy here. Something, right? Okay, so that intelligence about information. And in a way, that has a lot more with what a lot of you will try to do in your sort of innovative or entrepreneurial endeavor. Finally, the last word of intelligence is about, well, literally what you would think of being smart, clever, better, optimize, optimal, right? Optimal, right? So better doesn't always mean the most or the extreme. Okay, but a lot of time it is. For example, if you're going to travel from your home to the office or to Chulalongkorn University, hopefully an intelligent Google map would link you to the path that takes you the least time, right? Because there's combinatorial. You can take this road and then that road, take a fast highway, but it's a long way around. Or as opposed to short way, but it's, big traffic. So it's about intelligent solution, okay? And in the self-introduction, I told you that I came from that background, okay? My Ph.D. at Imperial College was in computational intelligence. It's about getting the computer, okay, to solve more difficult problem. Difficult in the sense that it looks intuitive to human being, but it's a solution in 50 dimension, right? Okay. And in a way, that spirit is what lives on in all of AI. If you think about it, this is kind of funny. You want AI to be super capable, okay? What do you mean by that? You actually don't really want AI to do something you wouldn't do. But you would want it to do something that conceivably you could do easily in 3 dimensions, but in n's equal to 500 dimension, you can't imagine. It's a little bit like that, right? So you don't want AI to, have its own agency and think about ruling the world or anything like that. You just want it to offload your task, okay? By the way, in that sense, AI is close to the word robotics, and the word robotics came from, anybody knows the original? The word robot? It's like there's a play, a Polish, I think, a Polish play. And the idea of robot was some machine that does the boring stuff, right? So we want the robot to do the boring stuff for us, okay? And so in a way, that's where this generative AI world is going, okay? Except we want it to be creative and generative, but we don't want them to have funny ideas, okay? Right. So we start with AI, with I, and then we go with the word A, right? A is artificial, okay? So artificial means several things, okay? First of all, artificial just means it's created by hand, okay? Art, the word art, same word. The word art, artifacts. If you have friends from archaeology and they dig up some spoon from, 10,000 years ago, that's an artifact. It's an artifice. It's something that's created, not by nature, but by man. So artificial intelligence here is any form of intelligence that's created. How do we create it? Well, today we create it with digital computers. Okay? But believe it or not, 300 years ago, even before digital computer, they were trying to create an automaton in Europe, something that would have some intelligent behavior. So artificial just means something that's kind of created, but in a sense, the creation has to have some kind of reference. Artificial, yes, it's fake, but it's a good fake, right? It's a good fake. It's not a bad fake. It's good fake in some sense, okay? And finally, generative. So I write the word generative, G, last, and, okay, I gave you the story that 10 years ago, people didn't use the word generative AI. They just used the word AI for something, okay? And when this new thing called generative AI came, the old AI got a rename. It's called retronym, okay? And that retronym was predictive AI, okay? In fact, today, so in fact, this is so you got this thing that becomes AI, and this thing fork into GAI, and therefore, this is new, and so the O becomes predictive AI, okay? Now, to say new and old in this way might be misleading, like you can choose one or the other, but it doesn't work that way. In fact, this is a foundation for this. So inside GAI, you find a lot of engine that's based on predictive AI, okay? And in fact, that's the object of today's lesson, okay? How predictive AI works, and therefore lays the foundation for GAI, okay? Okay, now, I couldn't help but give you additional information, by the way. This used to be something else as well. Okay, and this O gets a rename, good old-fashioned AI. Okay? Now, I did mention this in a brief sentence, but I didn't make a big deal. But this AI, you know what that was? Rule-based. Rule-based, right? So if someone has a high temperature and low blood pressure, but does not have, did not sleep well last night, and then you kind of make a diagnosis. This kind of if-then was the first attempt to create an AI. That makes sense, right? It makes sense. Why? Because when we make reasoning, that's what we do. We apply this kind of like binary logic. When I say binary, it means like you come to a junction and you kind of like decide to go left or go right. Okay? Right? So before I decide, your country of origin, I would go left and right into Asian, non-Asian, let's say, right? And they separate this country versus, and so on. When you make enough two-way decision, you get to every single point, right? In fact, I claim, look at all of you, okay? I can identify every single one of you by creating a series of questions. Now, obviously, if I cheat, I just say, what's your student ID? And that gives you unique, right? But the three I'm going to do is say, are you a boy or a girl? So that already separate two groups, right? And I keep doing, wearing blue shirt, wearing yellow shirt, blah, blah, blah. Yes or no, yes or no, yes or no. Eventually, all of you will have a unique address, right? So that kind of reasoning is very natural to human being. That's what we do, right? So it would make sense once you have programmable computer that the first kind of AI reasoning like, okay? Now this is very important. You guys, in your age, when you think of generative AI, you think of something cool that's generated. Back then, the litmus test, meaning what constitutes a successful AI, seems to be reflects human reasoning, right? Again, intelligence is human-like. Human think this way, think by logic, right? Now, human may have three-way logic, not necessarily binary logic, but it's harder to program. So let's just make everything binary. So we do all this if then, if then, if then, if then. So that becomes sort of like this kind of symbolic logic kind of thing. And this didn't work. So it goes down to the road of being renamed, okay? Now, unlike predictive AI, which is still with us, this one is, I wouldn't say it's a dead end, but it belongs to a different universe now, okay? It belongs to a logic, okay, semantic kind of world, okay? Now, you can do a little bit of GAI on this primitive, but, that's kind of like a niche area. Anyway, let's go back a little bit, okay? So we got this GAI, very important, right? G versus P, generative AI versus predictive AI. A, what's A? Artificial as in human-made, artificial as in resembling real thing, okay? Eventually, artificial as in artistic creation, okay? And then you have the three meaning of I. So these are conceptual thing. Again, this is part of your GI literacy, is to understand more than a typical guy who say, oh, GAI is something that makes a fake video or something like that. Okay? Right. So the first thing I want you to recall is my very burdened, definitional, pedantic treatment, making sure you understand conceptual foundation of what it means to do GAI, right? What is the other thing that I did for the first class that was important? The other thing that I want you to remember, if nothing else, was that it had two timelines of development. One, I will call it vision, AI. The other one is language, right? Now, I'm because it's a review, I'm not gonna, you have the slide. I think I gave you the slides, right? Okay. So the two timeline, now, how does that relate to this? Well, if you think about it, this is about an engine. What drives an AI? Okay, that timeline is a little bit like based on application. Okay, to show that this AI works, it has to do the vision task. Literally use the word task, okay? Do the language task. Okay, then there are the other things. There are artificial intelligence that smell some chemical and make identification. Okay, so you can think of it as a nose task. Okay, but largely speaking, the world of development has two timelines in AI. They're not separate. They're together. They're kind of like parallel. Okay, but different kind of focus. So one is to get the computer to speak like a human. The other one is to get the computer to understand picture like a human. That's it. All right? Now, if I stop there, it could just be predictive AI. To make it more like a generative AI, it would be not only can you speak with me language, I can ask you to make up stuff, right? Make up poetry, okay? Or in terms of vision, instead of just I give you the picture and you say, oh, that's a picture of a frog, that's a picture of Elvis, okay? I do the opposite. I say, hey, I'm thinking of Elvis. What picture would that be? And then it generates, okay? Now, this is very important to your lifetime because you are at the point where this generative is just becoming real, okay? I think when Basai started, the first year Basai started, we had video of Will Smith eating spaghetti. How many of you remember that? Yeah. That was when Basai started the program. I think it was about the same year. Terrible, right? A terrible Will Smith eating spaghetti, right? Maybe even around that time before that, we had fake Barack Obama, that sort of thing, right? I don't know if you remember that, deep fake, okay. So now we can do all kind of stuff, right? Now you can make Barack Obama not only modify his video, you can actually make him your avatar, okay, right? So it's almost uncanny what happened between Basai batch 001 and what you guys batch 007, right? Right? It's amazing. Anyway, so that second timeline, okay, is vision but in terms, now this is very important, in terms, so let me put this one down as logic or symbolic. Let's put it symbolic better. Okay, symbolic. Okay, now this symbolic is kind of like this. It's kind of associated with the language AI people. In other words, people with that pursuit, AI to do the language, because, after all, right, if then, it's a language kind of task. If I have high temperature and low blood pressure and no sleep last night, am I sick or whatever? Okay, so it's kind of language kind of task. Now this picture is going to get slightly complicated. Here's a vision, people. Okay, now the vision people tries to create a neuronal model of, remember, cat. You guys remember that? The cat, right? The cat. Okay? So, you can think of it as the thing they work with is not logic. It's not linguistic logic. It is some kind of mathematical model that mimics a cat's brain. Okay? Now, next class or the class after, I'm not quite sure, literally, I will teach you what's called convolutional neural network, basically that very model that it culminates in. Okay? But, so for now, it's sort of like a math model of nerve cell. Yeah, nerve cell. So it doesn't look like it's touching anywhere yet, right? Now, there's a third timeline. Well, I wouldn't say it's a third timeline. I mean, everybody's doing together. It's a focus, right? Imagine that instead of being motivated by the AI that do vision tasks or AI that does a language task, right? AI vision task, interested in what cat's brain looks like. What if you start from the brain itself? Hey, now we can call this a third timeline if you like a neuroscientist model. Okay, so it's trying to say, how does a neuron work? How does the cell inside a cat's brain work? In fact, this guy didn't even care about cat anymore. Okay, the cat thing was just there because it was very much a focus on recognizing mouse, right? It was a vision thing. So let's have a pure, okay? Now, I'm going to use a word which is not standard, but I'll hold you to it in midterm. Shall I? Yeah, let's do that. It's called connectionist AI. Okay? So, instead of focusing on AI as something that does language, instead of AI that does picture, vision, how about AI that makes connection? In particular, the connection is what gives it the power of thinking. And where would you get that idea? Literally your brain. Okay? So in a way, this is kind of like not just cat anymore. Now, why is this important? Because all this is this track. Okay, so remember this picture. It's kind of like, okay? Now, I'm going to put an abbreviation that I'm going to explain later. It's called ANN. So you can take a picture of this if you like. Maybe I should take a picture of this. Just so I can read it. Okay? Okay? Now, I'm going to clean this up. I'm going to clean this up. I'm going to clean this up. Okay? In fact, not only am I going to clean this up, I'm going to focus strictly on this guy. Okay? I'm going to erase now, right? Okay? Okay. So, open up your brain, or anyone's brain. Okay? It might surprise, well, it wouldn't surprise you because you are an adult, you are educated, so you know about what the brain looks like. But imagine that you are a child, right? And the child has been playing computer games on a computer. So he's used to the idea that when I open up the computer, there's some kind of central thing called CPU that does all the thinking. Everything else is peripheral, right? And this thing does all the logic. So if that child were to imagine what the brain looks like, he'd probably think that there's some kind of a core middle engine that does everything, right? Well, he'd be very disappointed because when you look at the real brain, there's no such thing. The brain is literally a mass of tissue. It's like your belly, where a whole bunch of cells looking very similar. There's no boss. Well, there is at some point, but I'm just making the point. So what's going to happen is when you look at the cell of the brain, it's just going to be neuron. Okay, neuron. Okay, basically it's very messy. It's connected to other neuron. Okay, very messy, very messy. So let's build the word. Again, I like to give you the intuition, so I literally will go alphabetical, one word, one alphabet at a time. The first thing I want to do is to say this is a nerve cell. Nerve cell is called neuronal cell. So let's write the word down. Neuron. Anything that has to do with neuron, anything that has to do with your brain is neuro. That's why you have neurosurgeon, right? Right? Neuro. Okay? However, like I said, unlike a computer where you have a core calculator, core logic thing, when you open up the brain, there's no center. It's just a bunch of connected, right? Now, certainly some neuron may be more important than the other, like in social network, right? Some friends are more important than the other, maybe, to a network. But that's exactly what it is. It's a network. Okay? It's a network. It's a neural network. In other words, it's a network of neurons. A network of neurons. Very important. Very important. Okay? Now, in order to back to that guy, that symbolic AI. Symbolic AI is just trying to replicate the reasoning of a human being using semantics, right? If high temperature and no feet, whatever, right? It's using symbolic, linguistic, symbolic, and semantic to replicate the human reasoning. However, when you write the syntax, the symbolic language, there's nothing biological about it. It's not inspired by biology. It's inspired by logic, right? So what if you want to make a AI model and you want to be really, really realistic? You don't want to just replicate the behavior. You want to replicate the mechanism. This is where we get a little bit more brave. Okay? Now, I'm going to make a sidetrack. One sentence, ignore, don't listen to me. I teach quantum computing on Thursday. You know how the field of quantum computing came? Not to crack codes. It was because we were using digital computer to study quantum phenomena. So quantum computer was to say, if what we want to study is quantum, the thing we use to study better looks like it. That's the original motivation for quantum computer. To study a quantum system, the thing you use to study, i.e. computer, better behaves like a quantum thing. Same here. To replicate a human reasoning, instead of just having if and then, if and then, if and then, we better start from the ground up and make sure that the basic component, the Lego bricks are actually the same analog as a human brain. Right? That was the brave stuff. Okay? That's the brave stuff. Okay? Now, you don't think it's big? It's a big deal. It's a bit like, those actors Hollywood who like to do this method acting. Instead of just acting, I want to live the life, man. Right? It's that kind of thing. To replicate something, it's not enough to just have external behavior. You have to be it. Right? Right? To study quantum system, the computer better be quantum. To study human brain, the model better look like a human brain. So this if-then doesn't work anymore. They literally want to make an artificial version of this. In other words, they can retroname the brain as biological neural network. So when I ask you on the midterm, what's another name for a brain? You have to say a brain is a natural or biological neural network, so that you can understand everything about the modern technology, everything that you do. Okay, all the way to ChatGPT, diffusion model, everything is built on a model, an artificial model of a network of neurons. Okay, so if I'm going to say what's the foundation of the modern world, some of you may say AI, some of you say this and that language model. I would tell you this: it's artificial neural network. Okay, it's artificial neural network. Okay, so this one is called artificial network. Now, you remember three meanings of artificial, right? The first one, you can't find it in nature. We have to make it. Second one, when we make it, it better looks like the real thing, resemblance. Third, it leads to artistic creation, like open ed. It can do things that wasn't there before. It's like artifice. Okay, so this better become, but this is a B and N. That's an A and N. Okay, that's it. That's the conceptual part. Now sit with it for 5 seconds. Make sure that it doesn't leak out of your brain. Okay. Now the world could have been different if the logic people, the symbolic AI, were successful. And to be honest, it was successful for a time. For example, for playing chess, I think it was. And medical diagnostic is still with us. In fact, if you have friends who are studying medicine, large part of medicine is diagnostic. And diagnostic engine still looks a little bit like this in a lot of cases. Okay, that's why you can have this kind of like a cheat sheet for things like COVID screening or disease if temperature above the blah blah blah, right? Or screening for heart attack. So this is all if then. Okay, so in medical field it still helps at very basic level. Okay, so now you understand this picture, right? So again, I gave you the definite meaning of GAI, starting from I, then A, then G. Okay, each component you'll be held accountable for, I guess in midterm or some point, right? I gave you the timeline that focus on, it looks at vision and looks at language, right? Now I introduce the concept that original thing is not just cats anymore, guys. Forget cat, right? We want to do human now. And in fact, that research, that core motivation became A&N research. Okay, in fact, that's what I wanted to do for my Ph.D., at least in the beginning. Okay, so A&N is, in one word, a mathematical model of a BNN. Okay, it's a mathematical model, but that mathematical model can become a computation tool if you can code it. Right? That's what we're going to do today. Right? We're going to code a neuron. Actually, we're going to code 2 neurons today. Okay? But first, we have to say, hey, the brain is really messy. Brain is really messy. So for the longest time, how brains are connected, it's like how roads are connected, right? You know the difference between Paris and London, right? Right? London is charming, but you get lost because the roads like God knows what. It looks like worms. Okay? Because it was inherited from medieval times. Okay? The city burned down. Instead of building it brand new, they built it in exactly where it was. So it's got this kind of funny thingy. Okay? Whereas Paris, they just make a straight line everywhere, and radial line and straight lines. Same with New York, right? Okay, well, think of a real human brain as looking at London map. Holy cow, it's really confusing, right? So let's simplify. Let's impose some kind of structure, okay? So for the longest time, there are competing structures. This, I will use the word architecture. Okay? When I was your age, the word was topology, but that word's kind of like died. So now we use the word archaeology. Archaeology means how are neurons connected? Okay? How are neurons connected? Now, before even we get to that, we have to say, what does a neuron do? Okay? So a neuron has to pass stimulus or pass electronic signal, right? So let's first think. I have a neuron. It looks like a cell. So let's draw it as a circle. It's connected. It's connected. Some of connection can be thought of as incoming, right? Some of it can be thought of as outgoing, right? Incoming, outgoing. Okay? Now, for a reason that may not appear obvious to you right now, I'm just going to make it many incomes, one outcome. Okay? It looks like, hey, why we do that, right? Because after all, when you come to a junction, you can have many roads. But this simplified things conceptually, and in fact, this is the way it's built. Mathematically, you build things from this. I'll tell you why, if you want to know. The reason we do this is because the mathematics we use to is univariate function. Okay, but you don't have to care about that. That's hidden reason. So, a neuron looks like this guy, has signal coming in. Okay, now it's a model, so I don't have to do weekly anymore, right? I can do straight line now. It's coming in, it's coming in, it's coming in, it's coming in, and it's going out. Okay, coming in, coming in, coming in, going out. Many to one. Okay, what is this mathematically? Well, if you think of, can I look? Okay. Input, process, output. You see this, right? That's where production looks like. However, mathematically, we write y is equal to f of x. Y is equal to the f of x. What's y? What's y? There's my y. Okay, what's f? There's my f. What's x? There's my x. Okay, in which case I would say this is x1, x2, x3, x4. Yeah? Okay. Now I will introduce the word dimension of the input. Dimension is like, well, if I want to find you guys, in this room, okay, how many numbers do I need easily? Well, like in a concert hall, right? 5th row, 3rd, whatever, 2 numbers. Yeah? So this is a 2-dimensional space. We live in a 3-dimensional world, but because everybody sits on the same floor, I don't have to worry about the vertical, right? Right? In fact, I mean, the hall can be this way. I still use 2 numbers. Well, likewise, here, how many numbers do I have? 4. Okay? So the input dimension is 4. Okay? Now, in real neuron, the input dimension can be 50 because neuronal cells are like that. Okay. So, okay, I like to keep repeating. Biological neuron looks messy. artificial neuron, you want it to be realistic. You're more realistic than the logic people already. But you can't be like, London, replicating London. You can replicate London by pretending it's Paris or New York. It's a bit more orderly. And that's what they do. Okay. So what do I have to do to make the model A? Well, I have to, for example, decide how many neurons are going to be. Right? How are they connected? And that's the word that we used to call topology, but now we call architecture. And how does individual neuron do the F thing? Right? The function thing. What does it do? Just add it up and just pass it on. Okay? That's a little bit simple. Maybe you should do something more fancy, but not that fancy. Can't be that fancy because we have a billion of them in here. You can't have a billion complicated fancy stuff. You have to have a billion simple neuron. Okay? A neuron has to be completely stupid, but a billion neuron is smart. Okay? That's why it's called connectionist philosophy. Okay? You connect enough. It sounds a little bit silly. It's like you connect enough stupid people, you get smart person. I don't know. It doesn't work that way. Pretend that analogy works. Okay. Now, this one neuron, okay, once I specify a bit more, I will trademark it, like I name it. Okay? Because it's my neurons, my model. Well, the guy who did it, named it perceptron. Don't ask me why. Okay, but this is not perceptron is not just this. You have to specify a few more things. But just get to that word. So instead of biological neural network, we want to create artificial neural network, artificial network of neuron. Each neuron now is modeled by this thing called perceptron. And the perceptron are not scattered everywhere. However, they are structured, they are organized into layers, like layer cake. Okay? And then you have more than one layers. So if I were to name this, like trademark name this, what would be a good name for it? It would be multi-layer perceptron. Okay? We will do that today. So how does it look like? It's gonna look like this. This is my input. However, I want to organize them into layers, right? So I have more than one. And I call this a layer. But wait a minute. I just told you I want my layer cake, right? So I would have more layer. So in fact, instead of drawing the output very far, I just draw my output over here. And then I would use this as input. And there's a layer. All right? Can you guys see that? Now, this has a well-structured sequence. What's the input to the first layer? The first layer makes an output that becomes an input to the second layer. Second layer becomes an input to the third layer. Okay, this is kind of like you can say it's a mathematical convenience, but it works really well. And to be honest, modern neurology, neuroscience, looks at the brain, and the brain is not that random. The brain also has layer organization. Okay, it's much messier than this, but it certainly is not like a random spaghetti that I was drawing in the beginning. Okay, So it does have a little bit of layer, and in fact, there's like a command center of the brain, and there's a, like, you know, sensor. So there's more architecture in here. Okay. So when I was saying that the brain is a bunch of tissue mingled together, I was exaggerating. Okay. Multi-layer perceptron. Okay. So what's a multi-layer perceptron? The sort of like answer you cannot go wrong is to say it's a particular model of artificial neural network. It's an artificial neural network model, a particular brand, as it were, right? A and N is like a car. Okay. MLP is like Toyota. Okay. It just happened that Toyota, you know, is everywhere, I suppose, you know. Yes, there are Subaru and something more exotic, right? But
like control questions, because the other side is there are a couple of guys falling asleep. So
okay.
Hello, this is Marco speaking. Okay, so
Here, but
yeah, just one. Yeah, yeah. Okay, so y equals fx, right? What do you need to do this with neurons? How many neurons? Typically, if that's a linear function, something kind of, you know, add one or multiply, something like that. How many neurons do you need for that? Make a wild guess, please. Simple function. These ones you have been doing since like high school. It's kind of clever to say it depends, but really in the most obvious thing, that this could be really like a multiply by 2, something like that. You want to do this with the neural network, you don't want to make it too complicated. What do you need? It's a simple linear function. Pardon? Yes. Yeah. That's not bad. Yeah. Okay. You need then a couple of inputs over there. So not only x, but you would need x1, x2. The other one representing the x and the other one m. Very clever. Okay. That's doable. But as a principle, you do this one simple function. How many neurons do you need? Surprisingly, only one, because, well, again, it depends what's your terminology, but this is, you can really do this with only one thing that has a threshold. You have input, and then you kind of compare it with the output. So doable. Okay. So how about if we want to do this? So why do we want to have multi-layer perceptron? I'd go and ask the other room. I think this will actually carry. Guys, I'm proud of you. A few of you actually took notes, but now I need to ask, why multi-layer?
why do we need to have multi-layers? In the other room, it just explained that simple functions just one neuron. Oh, yeah.
What was the thing? Why the guy inventing perceptron? He drank himself to death. Why? I'll ask the other. Why did the original inventor, one of the inventors of perceptron, why did he drink himself to death? What was the function that he couldn't do? Something we talked about last time. With a single layer perceptron, like with one neuron, you can't do XOR. And I think, Han, you told me last week that it's a function of what? You forgot, even though your answer was correct last week. It's a combination function. First you take one function and then you take another one. So, once again, you learn it from high school. Combine. Y is a function G applied to function F with the parameters, right? So, in order to do this, what do you need? Not one layer, because it can't learn things that are not linear. XOR is not a linear function. Yes.
Read the support drive.
It was a mistake to accept guys who study engineering to this course. But no, it's a bit, yes. Yeah, it's a bit, I know that many of those implemented hardware things, they use XOR functions. But this is much simpler. So if one layer is enough to implement something simple like AND or plus 1 times 2, in order to implement something that has two functions, one operates on the output of the other. What's your impression? You might need exactly this. One more stupid control question. One of the most typical things that you want to do as a starting exercise is recognizing handwritten numbers. Here's the output layer. Output. If you want to recognize handwritten numbers, what is the size of the output layer? Come on, please make a wild guess. Handwritten numbers, yes? Yeah? Yes, exactly. The size of the output layer is indeed what is the possibility of your handwritten number being one of these, and there are 10 possibilities. How about what would be the size of the input layer? Yeah? Many, yes. It's kind of the size of the pad where you draw the number. But okay, so sorry for the interruption. Let's carry on.
Yes, keep that in mind. The dimension, the input, in a way, you can almost think of this is one dimension. There's also the dimension of this. There's also the dimension of that. And the final dimension, in a way, is dictated by the application, right? In other words, conceivably, I can have, 100 of these, right? But at the end of the day, like Marco said, if your job is to identify digits and there are 10 possibilities, then output should be something like a light corresponding to 0, corresponding to 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And make sure that only one light lights up. Okay? Because that's the job. That's the job. That's the job. That's the identified number, right? What about identifying cat versus dog? Well, you can have a cat light and a dog light. In fact, you might as well save some money and just make one light. And that light is dog. So if it's on, it's a dog. If it's off, it's a cat. Right? Very good. So, now, okay. I'm hinting something here. Okay? I have been hinting that a neuron is stupid, but a billion neuron is smart. Okay? And I have shown you that one model of a neural network is to put them in stacks or layers, right? So obviously, a billion neuron has to be organized either by making the layer really wide or making a lot of layers, right? A lot of layers, really deep, 10, 20, different 30, 40, 50 layers, right? That way you can pack in a lot of neurons, okay? And there are mathematical reasons why going wide or going deep makes sense, okay? But the point is, it's got to be big, right? It's got to be big because you have to pack in. So basically, and this is something that you didn't need my class to know, when you talk about the size of the large language model, remember? You want to download something, and Olama or Claude, this is a Claude 7 billion parameter. Well, the number of parameter directly is proportional to the number of neurons. So the bigger the model, basically, is not smarter. It's like the strongest guy doesn't have better muscle fiber, that doesn't have better muscle cell. The strongest man in the world and a baby would have as much strength per muscle cell. Okay, I don't exercise at all, or I exercise a lot. My muscle cell has about the same strength. Strong person just has more. Okay, so in fact, we are going to encode today. I'll give you guys a break a little bit on Mathematica. Maybe 3 neurons. But that neuron is perhaps just as smart as the largest large language model, except they would have a billion or a million of them. Okay? Does that make sense? Now, generative AI literature means you understand where we're coming from and how things work under the hood. And today we'll see exactly how the neuron works. From 1 neuron, and then 2 neuron, and then 3 neuron, and then I'll say ... a million neuron. Okay? Because I want to show a million neuron here. Does that make sense? That's a good plan? Good plan? Okay? You should understand how things work. Okay. Now, I'm not complete. I wasn't finished with the specification of the function of the neuron. So let's do this. Let's write this again. Okay? Okay, I'm going to make output a little bit short because if you think about it, again, we can, have that. Okay, now, for demonstrative purpose, 2 is just as good as 4. So I'm going to start with just 2. Huh? Okay? Right? You guys agree with my picture? Okay, this picture represents a function. Again, I'm going to do this mathematically, even though my inspiration is a biological neuron. But, I can only do it mathematically. So, this function is a 2-variable function, but it has only 1 value. Okay? In those of you who are engineers, you say there's a vector function and scalar function. This is called a scalar function. A scalar function just means you only have 1 output. Doesn't matter what it is. Doesn't matter how many inputs you have 1 output. Okay? So there it is. Now, Marco already hinted, right? We start to do combining the input. Okay? So, again, I don't want to go to symbolic AI. But if you think about it, let's start some reasoning. Let's start thinking. I want to identify cat. Now let's make dog because we already use cat. So dog. Okay. So what are the two attributes that you think makes a dog? So, just simple. One, it's this size. Two, it's friendly. Or three, it's, barks or whatever, right? So in a way, you don't think of a dog as a dog. A dog only comes to your mind when I start adding attributes. Okay, let me try something else. Instead of telling you a dog, I say, what animal I'm thinking of? Mammals? Furry? Let's go. Okay? It's got teeth, right? So once I keep adding an attribute, things form in your head. So in a way, this is how our mind works as well. Again, we talk abstractly that our mind works like a logic, if then, but even more simple than that, guys. Okay, before you are a medical doctor diagnosing sickness, you already say, hey, that's a woman, that's a boy, that's a girl. How do you identify this? And I told you that, in Buddhist speak, this is called sanya, recognition of what this is, cognitive function. Okay? This cognitive function, it's not a one element job. It requires a few things collaborating. It's got to be mammals, it's got to be fangy, it's got to go roar, 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 and then all that add together make a dog. So in a way, it is addition. Okay, let's try that, right? So let's try this version. Y is equal to f of x1, comma x2 is equal to x1 plus x2. Okay, this is a sum. Okay, you can do that. However, maybe some features mean more than the other. All right, that mammal doesn't really help much because you got a bunch of mammals. In fact, if I say whoa, you don't really need to care if it's a bird, because no birds do that, right? It's almost the most important thing. So there has to be some kind of weighting as in giving the weight, right? So how about this? How about, let's not do this. How about this? W1 x1 plus W2 x2. Okay. Cool. So now I'm going to do W1, W2. Okay. Right? Now, think of this. Think of it this way. Your brain is based on electrical signals, right? If you keep adding, then the output just gets bigger and bigger and bigger, right? So in a way, you can't really have output that gets bigger and bigger and bigger. So let's think of an individual neuron. It doesn't matter how much stimulant it gets, it can only fire or not fire. So in a way, you kind of want something like this. But you want y to, this is a mathematical notation, element of 0 and 1. And in fact, this is actually what happens in the experiment, right? Stick some electrodes in a neuron cell, a frog in this case, okay? And either nothing happens or it sends a signal. So it's a switch. Aha. So it doesn't work just like a simple sum. It starts with a sum, it adds some kind of weighting so that some factor means more than the other, and in fact that way can become negative, right? So it's a linear combination, but you don't send the linear combination out right away. You turn this into a stimulus, and that stimulus has to trigger a switch. So how about this? How about, instead of just this, I put f, some kind of g function. And that G, okay, we give 1 if signal strong, 0 if not. Does that make sense? Right? And then you can, so instead of having, yeah, okay, so first thing first, the input comes from many things because you need many attributes to come and help you make decision. So you're kind of adding evidence, but not all evidence contribute the same believability, let's say, credibility. So you add some weight. In fact, some evidence is negative, right? So if I have concept like meow, okay, you definitely negate that. So you multiply that by -1, definitely not a dog, right? So you have a weighted sum, but you want to stick in this F. So that F here is actually a G of all this. Okay, so there has to be some kind of function G that turn a switch, right? And biologically, there's this thing called threshold. So if it's greater than something, it goes 1, less than something, it doesn't fire. Okay, this is actually the neuron model of, I think, McCulloch and Pitts in 1950-ish. 1950-ish. They already had this model of a brain. Okay. However, let's do this. Let's say x1 and x2 becomes under W1 and W2, W1 x1 plus W2 x2. Okay? Now, I want this expression to goes to W1 x1 plus W2 x2 is greater than some bias or not. If it is, generate 1. Otherwise, stay 0. Does that make sense here? Right? So actually, you can think of this as a parameter. Now, I don't know if I make the point strong to you. A parameter is a constant that changes. A variable is a variable by itself. A variable is like x, changes, right? But a coefficient is supposed to be fixed. But you don't fix it until you get the right answer. Okay, so it's kind of like it's like a variable constant of sort. It's kind of weird. Okay, that's what's called a parameter. This, I want to ask, and this is, okay, I swear I'm going to put this on the midterm. I'm going to give you a bunch of things and ask you to count parameters. Okay, in this case, how many parameters have we got? We got 2 variables. We got 3 parameters. Okay. And how many output? 1. So, if I send you this on the midterm, you should say, Dear Ajahn Phumjai, I'm looking at this and I'm looking at 2 input variable or independent variable, 1 output variable or dependent, 3 parameters. Okay? So, right. So what I'm going to do is simplify life a little bit. By the way, W stands from the word weight, right? It's the weight of evidence. B is like a threshold. Okay? In fact, it used to be when I was your age, this was called theta. Okay, but anyway, so let me rephrase this to make life a little bit easier. Let's say W1 x1 plus W2 x2 greater than theta or not, right? Now, what I'm going to do is I'm going to put this on the other side, minus theta plus is greater than 0 or not. Same thing, right? Right? Now, minus theta, I'm going to call this thing because it's sort of like a freebie. A freebie is like a bias. I know engineer would use that word, right? It's something that's kind of like given. So, before you earn an A, I'm already giving you a C. You just have to do a little bit more work to get to an A, right? So you don't have to start from F or something like that. So I'm going to call this B. So B, W1, W2, B is called bias. Weight and bias are the key parameter of a neural network. Now, for simplicity, a lot of time they'll just use W0. Okay? It's like an intercept, right? Okay? So it's a constant term. Okay? So we got this. We got this. So let's make something really clear here. I want something like this, like this, like this, and like this. So what I'm going to do here is to say W1, X1, W2, X2, right? And then I have W0 for free here. And then I have the sum W0 plus W1, X1 plus W2, X2 is equal to total input. Right? And what is my G here that does all this? It's basically a function that looks like this. If it's greater than 0, it's a 1. If it's less than 0, it's 0. It is a step function. Okay? Is that simple? Simple. Come on, you have to say it's simple. Unfortunately, simple is not biological. In other words, biology is a little bit messy. It's a little bit smoothly. You can't have this sharp function. Okay? It's a little bit too harsh. It's like when you dive, if you know those things like in off the coast of Japan, they dive and they see some rock that's really sharp and say, that has to be man-made or made by alien or something like that, right? Because nature doesn't do edges, doesn't do sharp edges. So how do I do that to make it more natural? Well, I just smoothen it a little bit. Okay? So it's something that if it's greater than 0 and a lot greater than 0, it approaches 1. If it's less than 0, the input's less than 0, much, much less than 0, it approaches 0. And somewhere when it's exactly 0, it makes that transition. Why do I do this? Well, again, there are two gods here. One is nature. Nature doesn't like hard edges. It likes something smooth. Who's the other god here? Calculus. Calculus also doesn't like edges because it's not differentiable. Anybody awake now at this point about calculus being differentiability? Okay, it's very important, okay? Nature doesn't like hard edges and calculus doesn't like it either. So for both of those reasons, the model of the perceptron that I'm telling you about is not the McCulloch pit, okay? I think it's due to Rosenblatt, but anyway, it's this. So let's call this thing something. Okay, it looks like an S, and in fact, it's just a signal, right? 0 and 1 switch, signal, same kind of word. So I'm gonna call it a sigmoid function. Okay, sigmoid function. I'm gonna call it a sigmoid function. Now, in fact, mathematically, there are many ways of making this kind of like smooth. I'm gonna go with the brand called logistic. So there's another brand called hyperbolic, but I don't like that brand very much. I like this brand better. So I'm gonna call it logistic sigmoid. Okay? So one neuron Y is equal to logistic sigmoid, kind of weird function, Let's get this kind of function on, right? WO plus W1 x1 plus W2 x2, right? Now, don't get scared, but you should know this. Summation notation is coming, right? Because if I have 2, I can write. If I have 10, my hands will get really tired. So what I'm going to do is, it's going to be this kind of like funny function of sum I going from 0 to n W I X I, where XO is equal to 1. That shouldn't scare anyone, right? Simple, right? Yeah, easy. It is easy. It gets more complicated, but if I open the book on neural network, you start with this, it looks scary, but I start from simple thing, then it doesn't look scary. Yep. A theta is, so it's a different way of thinking. The sum of W1 x1 plus W2 x2 has to be greater than theta. It's the same thing as saying that sum of W1 x1 plus sum of the W2 x2 minus theta is to be greater than 0. So I just call minus theta bias B. And most time, instead of have W and B, I might as well make B W0. Just a renaming. Okay? Just renaming. And that way, it's so convenient. And why is it so nice? Because in vector notation, what is a vector notation, guys? It's W transpose X vector. Right? Raise your hand if you know what this means. The dot product. Okay. Linear algebra for free. This is not a linear algebra class, but I'm giving it for you for free. You don't have to pay me. W0, W1, W2, 1, X1, X2. This thing is called a vector. Vector is a list of numbers. It's like a coordinate. Okay? Just like I said, where are you? That's a vector. Okay? So instead of saying, I go 3 steps to the right, 5 steps to the north, I say you are 3, 5. So you are that vector. Okay? So this is a vector, except it's 3 dimension. One of them is redundant. The dot product is this guy multiplied by that guy, this guy multiplied by that guy, this guy multiplied by that guy. And we write this as W vector has a little arrow. This guy is a vector, so it has a little bit arrow. This guy lies down, okay? Mathematically, when you feel like sleeping, you take a transpose. Okay, so this is exactly that. So when you open up a neural network book, it would say a perceptron is Y is equal to this funny thing, X transpose W. Oh, sorry, W transpose X, which is exactly the same thing. Okay? That's how you would see it. Again, a lot of mathematical notation looks complex, but you have to think of it this way. Mathematicians don't like to write. They just want to save their ink. Okay? Think of mathematician as somebody with big brain but very small jar of ink. So they always come up with a notation so they can write a lot less. Either they have, inks are expensive or paper are expensive, or both. Okay? Mathematicians always come up with notation. And you guys say, oh, what's all this weird notation? Just think of it as, poor guy, he's trying to do a lot of things with very little money. He can't buy ink, he can't buy paper. So he wants to make a notation that squeeze everything. So that's it. Okay? Now, it's a good time to take a 5 to 10, let's make it 10 minutes because, promise me next time you come in a bit early so we don't waste time. Okay? So let's take a 10-minute break early, come back, start your Mathematica. We will do this. Not only will we do this, we will do this. Okay? We'll do this together. Okay? Now go.